Good morning, all. Greetings from Jyoti Engineering College. Welcome to the International Online Workshop on Thermal Management of Electronics, which is scheduled on 27th and 28th July 2020. First of all, I'd like to welcome our speakers, Dr. Ajith Krishnan R, Dr. Uday Kumar G, Dr. Praveen. Good morning, all. Greetings from Jyoti Engineering College. Welcome to the International Online Workshop on Thermal Management of Electronics, which is scheduled on 27th and 28th July 2020. First of all, I'd like to welcome our speakers, Dr. Ajith Krishnan R, Dr. Uday Kumar G, Dr. Praveen B, and Dr. Kumareshan G. Secondly, I'd like to welcome all the participants to this two-day workshop on thermal management of electronics. Hope the workshop will be fruitful to all of among us. Now I welcome Dr. Ajith Krishnan R to handle the first section. He is currently working as a research associate in two-phase flow laboratory in School of Mechanical Engineering, Kookmin University, Seol, South Korea. He was an overseas research fellow from India as a part of Korean Research Fellowship Program sponsored by National Research Foundation of South Korea. He completed his PhD from National Institute of Technology, Trichy, in 2019 under the guidance of Dr. K.R. Balasubramanian. His doctoral research work was focused on flow boiling in micro-minute scale channels and their gravitational orientational effects. He has publications in reputed journals such as International Journal of Heat and Mass Transfer, Experimental Thermal and Fluid Science, Heat and Mass Transfer Springer, Experimental Heat Transfer Taylor and Francis, etc. His research area mainly includes flow boiling in microscale channel, thermal management of electronics, dehydrogenation, microreactors, and hydrogen storage. I welcome Dr. Ajith Krishnan R to handle this section.
Hello all. Whether nice is here? Hello.
Hello. Yes.
Nice, is it audible?
Yes, sir.
What about the screen? Is it okay?
Yes.
Okay, thank you. And great morning to all. And nice is my colleague. We are both on during my BTech days. And today, first of all, I would like to acknowledge my thank to Department of Mechanical Engineering, Jyoti Engineering College, for their effort in creating such a platform to present the research related things and different aspects regarding this thermal management. So I would like to introduce the first session. Generally, the topic we have given is the thermal management of electronics, or thermal management, simply we can say. There is a lot of methods that are available in order to cool the electronic devices, as you know all about the heat sink and some other methods. So in this session, we are dealing much on some general overview of this electronic cooling. In the coming sessions, we'll be in more detail with these different types. As basically, I'm going to introduce you one of the method, which is called as micro mini channel heat sink, which is used to cool very high heat flux devices. So I'm from School of Mechanical Engineering, Kookmin University, Seol, and I'm going to present regarding this general overview and cooling using micro mini channel heatsink. If you have any issues, you can interfere in between by using chat or some other thing if it is not audible or the screen is not visible. So I will try to include a lot of things which can be easily understandable to the common persons who are apart from mechanical department or some other interdisciplinary department also. So if you have any doubts, we can clear in the question and answer session, or you can directly mail me or WhatsApp, whatever possible to you. And I request everyone to keep you touch with these research content so that it will become more useful to you in your future career. So this is a general overview. First of all, how this heat is getting generated from an electronic device, the basic concept, and about the different cooling methods we will discuss. And later we will discuss about the concept of micro or mini channel cooling. How we can cool an electronic device or a processor or a chip by using this micro or mini channel. Next, the different research perspective, which can be very useful for some researchers who are going to start or begin their career in this area of micro channel cooling or electronic thermal management, and some of the references too. First of all, basically we need to know this concept first. From where this heat is generated, that thing need to be made clear before going in depth to this thermal management of electronics. As you all know, the main pumping device behind all electronic circuits is this transistor. And today we can able to make a transistor even 14 nanometer size. 14 nanometer. A small transistor inside your processor will be in the size of a 14 nanometer. You can see a transistor here. You can see simply a transistor here, simply a PN junction. It's a tiny switch that controls the flow of electrons. Control means it's binary, 1 or 0, on, off. It can allow the current flow, or it may not, or it will control the current flow. And a single transistor is 10,000 times smaller than a human hair, that is around 60 micrometer. You see how small a transistor was inside your processor. And inside your processor, a lot of transistors has been built in by lithography. Different stages of processes are there to create such of bulk transistors combinedly to form a processor. So the heart of all modern electronics is simply, we can say, this transistor. Next is this transistor density. How many transistors are there in a single processor or a single chip? The answer is quite simple, but it's uncountable. Actually, nearly 7 billions of transistors are there in a penny quarter of a dollar. It's simply a processor will be simply in size of a 1/4 of a dollar, 1/4 dollar coin, as shown here. You can see here the number of transistors that is included in that size is around approximately equal to the current world population of nearly 8 billions or 7 to 8 billions of transistors. See how much it was dense. 7 billions of transistors arranged inside a small size processor. So based on this density, it was in 1965 where Moore, Golden E. Moore, he was one of the co-founder of this Intel, who is the giant in processor making. He's observed one of the important law, that is what called as Moore's law. What he's observed was the number of transistors in a dense integrated circuit doubles every year. Each 2 years, the number of transistors will be get doubled. If today is 2 billion, after 2 years, it will be 4 billions. So this was the law proposed by Moore. And you can see the trend. It's true also. From 1965 to 2013, you can see the density of the doubling was exactly equal to Moore prediction. And from 2013 to 2020, the density or doubling was 3 years gap. Within 3 years, it will double. But still, the Moore's law is following. So the density of transistors is increasing day by day. So the size of the device decreasing day by day. So what will happen? So this is the next one. Why these electronics get hot? Simply, we already said that electronics as a base element transistor, which is a switching device which will become on and off according to, it will allow the passage of the current or not allow the passage of the current. Okay, the basic thought behind this generation of heat from these transistors is simply the second law of thermodynamics. That is principle of increase of entropy. Whenever there is an usage of energy or there is a transfer of energy, some amount of energy is lost as waste heat. If current is going through the transistors, or if it is not allowing the flow, there will always having an energy transfer in between or energy use in between. So according to the principle of increase of entropy, the second law of thermodynamics, it will generate a small amount of waste heat. This waste heat is unavoidable in any case. That means if it is unavoidable, that become a violation of second law, which is not at all possible till now, and it will not be possible as per my observation. So these transistors can generate heat due to this extra current. If we need more processing power, if you do a lot of things, gaming, copying, some other things, you are designing something, a lot of current will flow into a processor and more of energy will be used. At the same time, this will create a large amount of heat dissipation from the processor. Even though thinking it was easy, simply switching on and off, but see, the amount of heat that is generated from these 7 billions of transistors is very, very high. And it was dissipating only through a small few square centimeter size. That means the size of a processor, maybe 2 centimeter close 2 centimeter. So you can expect how much heat it was. If you are not having a knowledge how much heat it was developing, we will discuss that also. Is it that hot? Is it that hot? Yeah, it's too much hot. Even to cook a meat, you see, a raw meat was cooked by a Japanese YouTuber on his old AMD processor. See, it's possible. It's possible to cook meat. So you can expect what temperature it was increasing or how much heat flux. Don't try this at your own lab or somewhere else. This may be a used processor or something else. But it's possible. It's possible to cook. It's that much hot as you expect. So these are the general background of the heat dissipation from different processors. You can see there is an Intel Core i7 4790 processor, which having a 4 gigahertz speed. It was introduced in 2014 by Intel, and it has a thermal design power. That means the maximum power dissipation from a processor, and it was around 84 watts. You can see in 2014 it was 84 watts, which will be nearly equal to, when we calculate the transistor packaging size, it will be nearly equal to 60 watt per centimeter square. An electric heater will be having some 20 to 30 watt per centimeter square for boiling water. You see, this much heat is developed at the core of the processor. It's very much heat enough to boil water if we keep it for a long time. So you can see in 2019, the latest processor, Intel Core i9-10980. It's an extreme edition processor, which having 3 gigahertz and 25 cache. You can see here the TDP is 165 watts. It's doubled the amount of heat that is dissipated from the 2014 case were Core i7. You see the heat flux here is 100 watt per centimeter square. This 100 watt per centimeter square is what called as high heat flux. It's very much heat flux is there. And definitely we need to keep the CPU temperature at nearly 90-degree maximum, because it will lead to another issues of semiconductor resistance increment, breakdown, or also the melting of the different solders inside the device also. So the future requirements of high performance computing is around 200 watt per centimeter square. This much amount of expectation we have. We need to cool this much. In desktop computer, it was 450 watt per centimeter square. Okay. And before all that, in 2011, one of the Oracle Corporation, they have produced one computer which has a processor. Spark T4 processor. It has a maximum 240 watts TDP. That is 240 watts is generating from the processor. You see, 240 watts is getting generated from a processor. How much hot it was during its working. The prediction is generally by 2026, which will be 6 years ahead, the amount of heat generated from the processors will be nearly 800 watts. That's the title of the slide too. 800 watts heat dissipation by 2026. 800 watts need to be dissipated from a processor. How we will dissipate? There comes the role of thermal management research area, the thermal management of electronics, how to cool these devices effectively. So we will see how to cool these devices effectively. What are the different methods that are available in the existing scenario. You can see these are the different electronic cooling schemes. There are conduction cooling. You can see there is a conduction circuit. Simply by using some heat conduction material, we can able to cool the device by graphene sheet or some wedge lock technology and other things. The basic principle is simply conducting the heat to the metallic bar or metallic material. Okay. Another cooling technologies is thermosiphons. It's a closed loop. Next is heatsink. You can see when you open your desktop, there is a fan attached with a heatsink in order to cool your device. Fan and heatsink, heatsink and heat pipe. Heat pipe is another important device which has been built in your mobile phones and all in order to cool. So another one is the advanced cooling technologies, cryogenic cooling, refrigerant cooling, immersion cooling, simply immersing the electronic device completely or servers completely inside the coolant. This is another method. Hybrid cooling, this microchannel cooling, miniature channel cooling. So heat transfer coefficient will be very high. Spray cooling, cold plate, a lot of different cooling methods. Phase change material, compact heat exchanger, heat pipes, vapor chambers. A lot of cooling methods are available, which can even be taken as an elective subject also. But our target is to mainly concentrate on some of the basic methods of electronic cooling, which was widely adopted all the places. So we have selected this course accordingly. You have the basic idea of microchannel cooling here. You have the basic idea of immersion cooling, pool boiling cooling. You have the basic idea of phase change material based cooling. You have the basic idea of heat pipe based cooling. So these sorts of cooling technologies will be covered in this workshop, in these 4 sessions. And first of all, we will deal more in detail about this microchannel cooling. This is a graph showing how much heat flux can be removed from different cooling technologies. You can see the basic air cooling. You can see this air cooling, which was basically used in your normal desktops. A fan will be running and heatsink will be there. It can carry heat only up to 50 watt per centimeter square. Okay, only 50 watt it can able to handle. And high technology future cooling devices can able to dissipate up to 250 watt per centimeter square, maintaining the chip temperature at around 85 degrees Celsius. So these cooling categories are mainly into 2. We can see passive cooling and we can see active cooling. This passive cooling is simply without the use of an external power. You can see here a passive cooling here. Simply on the top of a chip, we will place the heat sink like this. It may be a copper, aluminum, or according to that optimized material. Cost optimized and performance optimized material, and you can see it simply dissipate the heat to the surrounding air. This is a passive method without using any external power. And this phase change material cooling, which Praveen will take later, that will also falls under this category. And Kumaresh sir will handle later about these heat pipes. That is also falls under the category of passive cooling without external power. Now the another case of cooling, you can see this active cooling. We will adopt some fan or some external device in order to improve the convection coefficient, heat transfer coefficient. Okay, this is the active cooling. You can see a fan here and the chip is here. Simply a heatsink is here. This fan will force convect the heat from the electronic device through this heatsink. So this is what called as the active cooling by using external power. These are the main categories of electronic cooling, passive and active cooling. So first of all, we will see how this base electronic cooling by using a pin or by using some heatsink will work. It's simply by using this device, what called as heatsink. You can see here. This heatsink will be attached to the processor by using some paste, what called as heatsink compound. You can see heatsink compound when we open your processor and your fan. In between, you can see a brown paste. That is what called as heatsink compound. It is in order to prevent the air gaps from the two surfaces of contact and hence to reduce the contact resistance of the surface. So heat can be easily dissipated. And this is one of the model of that simple electronic cooling by pin-fin heatsink. You can see here showing the resistance model. The three resistance. One is interface resistance. The other one is the resistance of the heatsink, and this is the resistance of that chip top surface. So it's simply the natural cooling of by the air, simply natural convection, and the heat transfer coefficient will be very less, nearly in the order of hundreds, and also the maximum heat that it can dissipate will fall around 10 watt per centimeter square and 20 watt per centimeter square. Maximum 10 to 20 watt per centimeter square we can dissipate by using this, but our requirement is around 200 or 300 watt per centimeter square. So this is not an efficient method, and in which need to be revised according to the new device level and device performance in order to dissipate more heat. Okay. So the another method of cooling came, that is what called as liquid cooling. In this case, the liquid will not allow to contact with the chip directly. Here what they will do is they will provide a cold plate. You can see a cold plate here at the end. You can see two cold plate here. The cold plate will be like this, a flattened plate along with the tubes are attached. This will be a single surface, and this will attach to the processor surface. So what will happen? The fluid will be flowing through these tubes. Along with that, it will take away the heat from the block and also from the directly from the tube, and that liquid to be cooled by using a heat exchanger like this. This is what called as liquid cooling method by using a cold plate. And since here also the liquid is not in direct contact, and the transfer coefficient will be less. So what's next? Have you ever seen this type of a cooling technology? This is what called as heat pipe cooling. You can see the same in your phone. If you open your mobile phones, here you have an example here, a Poco F1. This is a Poco F1 phone backside. You can see this is the place where the processor will be stacked, and you can see a small copper strip here. You can see a small copper strip like this. This is what called as heat pipe. This heat pipe is in order to remove the heat from the processor. It has a major three parts such as evaporator, adiabatic, and condenser, and it can able to dissipate heat. How the heat pipes will work and all, I think it will be detailed in the coming sections by the Kumareshan sir, because he is an expert in that area. So you just understand it is more efficient cooling method, because the heat transfer from the surface is more effective than a normal heat sink. It having a wick inside in order to take away the liquid. Some amount of liquid will be filled inside the heat pipe in order to carry away the heat from one surface to another surface. It will be detailed in the coming sessions, definitely. And some other phones, Galaxy S7, Sony Xperia, and even Microsoft Lumia 950 XL, all these phones are adopting this type of cooling strategy in order to cool their processor. So next one, the graphics card cooling. Actually, we have the gaming stations or some workstations in our departments, labs, and homes in order to do a lot of activities such as video editing, graphics design, a lot of things. In graphics card cooling, actually a combination of heat pipe along with fan cooling is used. You can see the heat pipe here. This is the heat pipes which can be spread along, and you can see the fan here. This will be fixing on the top of this, so that both heat pipe along with fan can able to cool the device effectively. So this is another cooling method. This is one of the interesting area of cooling, that is what called as immersion cooling, or it's basically worked behind pool boiling. Simply immersing the entire electronic server or the module inside a pool of liquid. Have you think about that? Simply inserting an electronic device in a pool of liquid. Yeah, it's possible to cool devices like that, because some server boards, server chips, and other things are manufactured in a way such that it can be directly employed in immersion cooling by using some particular fluids. We will call it as electronic fluids. Such type of fluid can be used in order to cool the servers and all. Simply we will immerse the device inside the coolant like this. You can see here, simply immersing the chips inside the cooling, and the heat will be removed by a coil from the top side if it is evaporated. I think Dr. Uday will take more on this pool boiling based concept of heat removal. It's working phenomenon behind this is simply pool boiling. It's some sort of two-phase flow, and that will introduce more heat to the working fluid from the chip, and that can be taken back by using a condenser coil. It's immersion cooling. This is another method to cool data centers and servers. Next is another one, that is phase change material based cooling. You can see the space between these fins will be filled with a phase change material. You can see here, usually the paraffin, different combinations of other materials. So what will happen? While absorbing the heat from the processor, the temperature of the phase change material will increase, and gradually it will melt, and its melting point will decide the temperature. So gradually we will get some sort of a curve, and also it will cool the device effectively. So this is phase change material based cooling. Now coming in detail to our categorization of cooling, it's one of the important cooling method, that is what called as micro channel based cooling. You can see here a processor or a chip is here. Simply a processor is placed, and over that we will make some heat sink so that it having small channels built on the surface. Okay, and through these channels we will allow the coolant to flow. You can see there is a coolant in, there is a coolant out. In this way it can able to cool the device effectively. So this is the basic concept behind micro mini channel based electronic cooling. By directly allowing the liquid to contact with the channel or to the processor top surface, and hence dissipating more heat. So first of all, we need to think, what's the channel size that I need to be chosen? So the channel size has an important role in this. Basically, the channel sizes are classified as different types like this. We have a conventional channels having greater than 3 mm. We have mini channels which falls from category of 3 mm to 200 micrometer. We have micro channels which will fall under the category of 200 to 10 micrometers. So basically, in the case of electronic cooling, we will generally use this micro or mini based channels. That means the channel size in the range of less than 1 mm or 1 mm to 3 mm. In that category only we will use. So what's the speciality of these channel size? Because that we will discuss later here. And this is the channel size selection. You can see here there is a conventional macro cooling, bigger size channel. You can see bigger size channel here. And this is some micro channel based, a large number of channels, that is miniature channels. What's the peculiar difference between these two cases? It can be simply narrated with an example here. You can see a simple cube here, which is divided into 8 divisions like this. See what happening here. This is the surface area is 6 centimeter. When it is divided into 8 pieces, the surface area has been increased to 12 centimeter. A drastic increase in the surface area with 2 times. So similarly here you can see a cube 1 centimeter, which has been divided into 100 nanometer, small cubes which has been divided, and the surface area has been increased to around 60 meters square, 6 centimeters square to 60 meters square. See what's the increment. So there is a drastic increase in the surface area if we reduce the number of channels or if we use miniature channels. So the basic concept behind that was surface area density. That is, for a particular allowable volume, what is the surface area? Or we will say surface area to volume ratio, surface area density. This parameter will decide how much effective your channel cooling is. So you can see the surface area density for a micro channel will be around 700 meters square per meter cube, which is good enough to consider it as a compact for higher or efficient cooling. So that's the peculiarity behind micro channel. It have more surface area per unit volume. With minimum coolant, you can able to cool the device effectively. So this is the heat transfer coefficient variation with the hydraulic diameter. If we use the smaller channel size, some bigger channel size to some smaller channel size, you can see here if we reduce the channel size, what is the increment in the heat transfer coefficient? There is a drastic increment in the heat transfer coefficient. Initially, it was nearly 10 for 10,000 unit, and later it has been increased to 10,000 for 10 mm hydraulic diameter unit. So with the reduction in the hydraulic diameter, definitely there is an increase in the heat transfer coefficient due to the increase in the surface area density. So this is the technology behind using of microchannel cooling, because if you reduce the channel size, more area per unit volume, and hence more heat transfer. So this type of channels can be employed to cool the electronic devices effectively. Okay. So this is the base behind the using of microchannel cooling. So how the microchannel cooling was adopted? You can see two types of strategies we will adopt. One is single phase cooling, and the other one is two phase cooling. We will call it as flow boiling. Okay, we have a processor here, which from the heat to be removed, we will attach the heat sink or some channel on the top of the processor, inside which the fluid will be flowing. You can see here there is only single phase flow, because the heat that is depicted from the processor is very less. So the water will, or the fluid will be remaining in the one phase only inside the channel. And this is the two phase cooling. You can see here the heat from the processor is high enough to boil the water. You can see here the heat from the processor will cause the water to boil inside and will undergo a series of phase change. You can see here the water is boiling off inside the channel. This is the another strategy of cooling by using mini micro channels. That is what called as two phase cooling, or we will say flow boiling. Okay. So while boiling, you can see a lot of patterns inside. Initially, it will be single phase flow. Then small bubbles will come. Then it will enlarge the size. Then it will be like a bullet shaped bubbles. Then it will be like a long annular flow. We can see a small thin film on the surface with some vapor on the center part. This is what called as annular flow. So in this way, two categorization we can use in order to adopt this mini or micro channel cooling. One is single phase flow and other is two phase flow. And nowadays the most cooling strategies was belong to this flow boiling, that is two phase cooling. Actually they are adopted because it can use both latent heat and sensible heat can be absorbed from the processor in order to cool it effectively. But a lot of issues are also associated with that we will generalize later. So how it looks actually, when you say mini channel, you has to be some thought of the channel size. How the channel size, how much it will be small. This is the approximation of that. You can see here there is a 1 rupee coin, an old 1 rupee coin, and you can see a small channels that has been as test channels that has been built on a small block. You can see, you can approximate the channel size here, how small it was. This was around some 0.4 mm opening only, and this was having some 0.5 mm opening, and this was having some 0.6 opening. You can see 0.2. This is 0.6. This is the range of the channel size that we have adopted in order to cool the electronic devices. And this is the sample that has been built on a copper block. You can see here a small channels has been machined on the copper block top surface. And this is the enlarged view by using a microscope. You can see here the channel size. It's very small. It's nearly 200 micrometer, which is nearly 5 times or 6 times thicker than a human hair. In that much categorization it will fall. This is how the channels will look like, that will be generally used for electronic cooling. So regarding the working fluid selection, the next doubt is which working fluid we will use for electronic cooling, whether water can be used or whether is there any some other fluids are available. Yeah, actually water can be used in case of electronic cooling. Many of the researches was based on water only, as it was a universal available fluid and cheaply available fluid. But generally water cannot be used as a working fluid in practical applications. Why? Because the dielectric constant is around 60 to 80, or the dielectric strength of the water is much less, because a high dielectric constant means it can able to be polarized when we apply the electric current, because we are using an electric circuit. So definitely electric current will be act as a disturbance in case of water. So there is a chance for intense breakdown in case of water. Chances are less, but still there is a chance for breakdown. So generally, water will not be preferred in practical applications. Instead of that, we will use electronic fluids. That is what called as FC72, HFE. HFE different categorization fluids are available. You can see. So generally, there is a category called as electronic cooling. That electronic cooling fluids. That is electronic fluids. You will say that can be used, or dielectric fluids. That also another term for that fluids. Dielectric fluid. So why water is not using means it's due to the dielectric strength was much less as compared to the other fluid. But performance wise, water has a good wettability, it has a good specific heat capacity. It is very much good in order to heat absorption. It can absorb a lot of heat when compared to the other working fluids. But the problem is that the dielectric strength of water is much less compared to the others. That's why we are avoiding water in many cases of practical applications. But still a lot of research is there with water. So what will happen if we use different working fluids? What will happen to the heat transfer coefficient? Generally, we can see the water will fall under the heat transfer coefficient range here. This is for a single phase flow. And here, this is an orange color will indicate the boiling. You can see the boiling here. See the boiling here. If water is used as heat transfer fluid in case of boiling, you can expect the heat transfer coefficient from, you can see 100,000, from 10,000 to 100,000 you can expect. That's the range of heat transfer coefficient if we use boiling as a mechanism of cooling. While in single phase flow, it will be nearly around 1,000 to 10,000. So see how powerful this boiling heat transfer was in order to the cool a device, or in case of heat transfer. It has an intense heat transfer coefficient, so it can able to dissipate a lot of heat from the surface if we adopt it for cooling. And the next one is the different methods are here, and what are the heat transfer coefficient ranges for different methods of cooling. Here also you can see there is a water, boiling, convection. You can see the heat transfer range, it's very high. The unit here is some sort different, but see the range is very high in case of water, from 1,000 units to 10,000 units. While in case of air convection, it is nearly in the order of 10 to 100. See how much ineffective was this air cooling, how much effective was this water-based boiling, two-phase flow-based cooling. So that's the peculiarity of different cooling methods. There are some another cooling methods which are extremely more powerful than mini channel or micro channel based two-phase flow cooling. That is what called as spray cooling and jet impingement cooling. You will see that later. See here. This is a extreme powerful cooling methods. This is the future level cooling methods. That is what called as jet impingement cooling and spray cooling. You can see this is the chip that is to be cooled, that is placed here, and this is a small micro jets that is allowing the working fluid to fall on the top of the chip. It will impinge the working fluid on the top of the chip, and hence it will allow the cooling. You can see this mechanism behind the jet impingement. Similarly, if there is a nozzle was placed here, it will allow to spray the working fluid on the top, and hence it will cool the substrate. You can see this is a mechanism of spray cooling. There is small tiny droplets of water particles that will impact on the surface, and it will form a thin film on the substrate, and hence it will cool the device. So these are all extremely powerful cooling methods which has been used in avionics packages, in fighter aircrafts and all. Research are going in order to implement these things in such devices for extreme high heat dissipation. It's more powerful than microchannel based cooling. So coming back to this channel based cooling, before any cooling scheme, we need to test those things, how the cooling device will perform, what size of channels, how it can be implemented. So this is the general pictures that showing the adopting of a cooling microchannel based cooling into a real platform. You can see a chip is cooled with a water inlet and some working fluid outlet. You can see here inlet and outlet has been machined on the chip surface. It will allow to cool the chip. Like that, here another PCB board on the top of a processor, we are allowing the cooling. But directly we cannot able to implement such sort of device here. Hello. Okay. Is it clear now?
Yes.
Yeah, okay. Sorry for the obstruction here. Okay, before adapting to the channel scheme, we need to implement our own trials, our own experiments before implementing to a real electronic environment. So this is our extreme versions. They have been adopted those things directly into some of the electronic boards. But generally, many of the persons we cannot able to do like that. We need to do a lot of trials and research, some or background works in order to simulate the electronics. So generally, we will test our cooling facility by using this as per you have shown in the schematic. You can see here the thing that simulates the electronic device is this part. There is a small heater block and all. We will create a small, we'll mimic the processor here. Actually, the amount of heat only we need. We don't need the processor clock speed and all. We are not involving to that. We just simulate the heat of the processor by using a heater and a small copper test piece where the channels has been machined. And we have a lot of facilities in order to allow the working fluid at a particular temperature we can input. We have a pumping device. We have to monitor the pressure drop. We have to read out the temperature, every data, and we have to input some power. So some DC power supply. These are the general scheme, how we will adopt the scheme of electronic cooling. Before going to a practical version, we will check the parameters by using a experimental setup. This is the basic experimental setup, and also we will monitor using a high-speed camera what are the things that are going to happen inside the channel while flowing. So this is the basic layout of cooling experiment that we are doing in labs actually for channel based or for any cooling experiment. It will be there. So this is the basic behind that. You can see a processor here. I am mimicking the processor by using a small device like this. This is what called as copper block, copper heating block. We can see on the top of the copper heating block only we will do our research work. Actually, we will machine channel, we will machine whatever the patterns we want in order to improvise the cooling or in order to improve the cooling like that. Okay, we have holes in order to measure the temperatures and a lot of things. And this is that section view. You can see here we have cartridge heaters. We, in order to heat up the small copper block, and we will allow the casing in order to arrest the flow of liquid to the sides, and we will allow some fluid inlet and we will allow some fluid outlet. Like we will test the performance of each channel inside this block. The fluid will come inside, it will pass through the channel, and then it will go out like this. In the meanwhile time, we will check all the temperature parameters, the temperature of the surface, temperature inlet, temperature outlet, pressure inlet, pressure outlet, everything we will check. And in this way, we will have a performance assessing the device of cooling mechanism. Later, we will adopt the same into the processor. Like that, the research will go on. Initially, we need to have some platform in order to mimic the cooling scheme, and later we will adopt actually. So this is the real-time view of that channel mimicking. You can see the small channels that has been machined here, and we have all other things, water inlet or coolant inlet or coolant outlet, whatever it is, coolant is used. You can test. These are pressure transducers in order to monitor the pressure. You can see the temperature sensors to measure the different parameters. This is the complete setup that actually we are using in order to check the channel cooling performance. Actually, this was built up in National Institute of Technology, Trichy, for our experiment. And the another important research aspect in micro mini channel based cooling was whether the conventional channel theory is valid, because we have already a lot of data regarding Nusselt number, fully developed flow. We have the friction factor reduction. Everything is available for conventional channel theory. That means channel size greater than 3 mm. Whether the same can be adopted in microchannels, that's the question. Actually, the question is still under research. We don't received any permanent answer to that, whether it can be adopted or whether it can be not adopted. Still a lot of controversies are existing on that. Some researchers are telling that both correlations can be applied to small miniature size channel, but some others are telling it cannot be applied. It depends. So the main difficulty is that the machining of the channel, because it will create a lot of roughness on the surface, and definitely these correlations may not be sometimes valid with the real-time performance. Here you can see here there is a single phase data reduction result from a 1 mm hydraulic diameter channel. Maybe some of the mechanical engineers know that generally we have studied for normal channels, whatever it is, the Reynolds number transition will be from nearly around 2300, that is from laminar to transition, and later some above 4000 it will be turbulent. Like that we have studied for the past many years. But see, for a channel of 1 mm hydraulic diameter, the situation is entirely different. See what is going to happen. It's during our trials we have observed this interesting fact, which was observed by many other researchers also. We have observed a transition within 1000 Reynolds number. Within 1000 Reynolds number itself, the flow becomes turbulent. That's the situation in case of small channels. That's why we need to explore more on these small miniature size channels, because the roughness will create a major role here. It will make the flow more drastic, and it will allow the boundary layer to separate and make the flow turbulent within 1000 laminar has been ended. So in this way, we can carry our research. Actually, we have done this experiment 5 years back during my MTech days in JECC Kozhikode. Actually, within 1000, we have observed the laminar flow. In this way, you can analyze your performance channel so that we can having a better analysis of the channel size. See what will happen if the channel size is again reduced. These are the different categorization of channel size. Different type of channels are the circular channel, square, rectangle, any size you can choose. All these having a different performance comparisons also is available. So this is the Nusselt number performance. This is the theoretical one, and this is the experimental one. See, the experiment one is falling where it's gone beyond 30 Nusselt number. Actually, this is the cooling performance of miniature channels. It has immense heat transfer coefficient and immense Nusselt number value. So it can be a best choice for cooling of electronic device, since it is compact in size, and also we can expect more heat transfer coefficient. Okay, that all is based on single phase cooling. Now moving to the two phase cooling. As previously we have explained usually in micro channels, the two phase cooling is more effective because here the boiling will occur. So how this boiling will occur? Actually, initially you have seen that is water is getting boiled from a surface. Initially there will be a small bubbles, and later these bubbles will be evolved from the surface, and later the buoyancy force will act and this bubble will depart from the surface. Actually, this is the boiling curve where point A is the onset of nucleate boiling, the starting point of nucleation, and at this point the CHF, critical heat flux, will reach. That's the maximum extreme point of boiling. Beyond this, if we go, the heat transfer coefficient will reduce and later increased by radiation heat transfer. So this point up to point B is the operating point of any microchannel cooling device based on two-phase flow. Beyond that, we will not experiment, because the entire fluid inside the channel will become dry out, become vapor at this point B. So this is the maximum extreme point that we can go by using this microchannel based two-phase cooling. So the main application behind this microchannel based two-phase cooling is on, we have the refrigerant boiling in your refrigerator, steam power plant, chemical industries, nuclear reactor coolant or supercomputers, and the main categorization is fall on this electronic cooling. this electronic cooling has a huge role because the miniature size of the channel has a huge importance. Okay, so the critical heat flux and flow instabilities are also some of the issues of this sort of channels. That's a detail we will explain later as a general view. So basically what will happen in a conventional channel, generally in case of conventional channel of greater than 3 mm, the flow will settle down. Actually, you can see here the flow will simply settle due to gravity like this. This is the vertical case where flow is allowing over the channel, and there is an extreme point. After this point, we cannot able to cool the channel effectively because complete vapor was there. So suddenly there is a hike in the temperature, you can see here. So up to this point is the marking point. Beyond that, we will not operate our device. It's an indication of that. So basically in conventional channel greater than 3 mm, you can see the flow will settle like this, and the heat transfer coefficient is also very less. So there is another category of channels which is less than 3 mm and higher than 200 micrometer. In that case, what will happen? That is called as micro channel, and we can see a good performance improvement in case of such channels. You can see the flow stratification was not observed in case of micro channels because the gravity force was completely neglected in case of micro channel, and you can see a small thin film on the top of the channel and also on the bottom of the channel like this. That will allow the cooling efficiently. You can see the picture here. You can see a small film will be always on the channel wall in order to cool the channel effectively. This is what called as annular flow, and this thickness is what called as annular film thickness, we will call. It has a huge role in cooling of the electronic devices. But anyhow, we cannot operate it beyond CHF. There is an extreme limit to all this, but this annular formation is especially for micro channel only, and this will be very less in case of conventional channels. So adopting a micro channel for cooling with two-phase flow has a huge importance is because of this thin annular flow that is available inside the channels during flow boiling. So generally there are two mechanisms of flow boiling in microchannels. When we adopt it for cooling, you can see one mechanism will be like this. It is what called as nucleate boiling mechanism. Simply, it will absorb the heat from the processor or from heat from the device, and it will boil. You can see small bubbles. The bubble will enlarge the size. Gradually, it will increase the size. It will increase the size. It will undergo a series of flow patterns. This is what called as slug flow. This is bubbly flow, and later it is converted to annular flow. This is the end point here. This is the end point. Beyond that, it cannot operate. Okay. So the heat transfer coefficient is also like this. It is a stable heat transfer coefficient, and after that it will suddenly reduce. Okay. This is the corresponding image. You can see a series of slug flows here. You can see a series of slug flows here. This is from our experimental results. So this is what called as nucleate boiling, one category of two-phase flow cooling. The second category is convective boiling. You can see here, previously it's bubbly flow. It's converted to slug. Suddenly you can see there is a straight annular flow formation inside the channels. The dominant flow pattern inside this case is annular flow. For very, very small channel sizes, this type of annular flow will occur, and that will drastically increase the heat transfer coefficient due to the small thin film that is available on the channel wall. So you can see the corresponding figure here. This is the straight annular flow that we have observed in our 1 mm channel. You can see here also, this is a straight annular flow that we observed. So this is more effective than compared to the nucleate boiling, but in general boiling studies, we cannot able to find a single mechanism. It's usually a combination of these two, combination of nucleate and convective as far as we have observed. But some researchers has been reported this sort of convective boiling dominant heat transfer mechanism. So this thin film is the major, as a major role in cooling the channel efficiently by using the water content that is getting evaporated from the surface. So what will happen at the end point? You can see at one point this thin film will break. You can see here this thin film will break at one point, And at the point, you can see there is a sudden increase in the temperature. You can see there is a sudden increase in the temperature. This must be avoided at any cost in the electronic cooling case. While we designing the mechanism, this point we must be avoided, and our operating point must be less than that. Our heat flux must be less than that. That is the maximum extreme point it can able to cool. So that point is corresponding to this point. We will call it as critical heat flux. You can see the critical heat flux, CH of, we can say. So after that, what will happen? The sudden decrease in the heat transfer coefficient will occur. So we need to be very careful while handling microchannels for electronic cooling, because at the CHF point, a sudden increase in the temperature occurs, a sudden reduction in the heat transfer coefficient, and that will lead to burnout. If you use such a thing in an electronic device, the entire processor will burn out. So it must be very careful. It must be deal with very careful, that operating point. So this is what called as the dry out in case of channel. You can see the white color inside the channel. It is completely vapor. You can see the classical dry out inside. 0.3 mm channel. This is a 0.3 mm channel from our research work. It's a complete dry out. You can see no water inside, complete dry out. So in a lab it is okay, but in a real-time environment, in an electronic device, it is not at all favorable. So we have already discussed with some of the basic things that about two-phase cooling by using mini channel or micro channels. Now a little bit of research point of view. I think many of the persons who was focusing towards this seminar or towards this workshop is mainly to getting something for their research work, or how they can use this seminar effectively, or this presentation effectively, so that it can be employed in their future research work. Maybe many persons are struggling with the literature in order to find something interesting in some areas. So from these slides onwards, I'm introducing some of the research possibilities in this area, in this thermal management by using mini or micro channel based cooling. So I think it will be interesting for persons who are looking much towards this area. And first is, the main target is to increase the heat transfer. How we will increase the heat transfer coefficient in a micro channel? It is always looking from the all electronic companies how to dissipate the heat. It will be a good area of research, how we can able to enhance the heat transfer in the micro channel and hence to cool the device effectively. So there are different methods. Passive methods are there and active methods are there. Active methods, we need some power, and passive, we don't need any power. So usually we will suggest the passive methods because it does not require any power. So the main element behind this passive cooling or this passive heat transfer enhancement is the fins. To increase, how to increase? Already the heat transfer coefficient area is higher in case of micro channels. Again, how we will increase the heat transfer coefficient area? We can do inside the channel by using small scale micro pin fins in the size of 50 micrometer or in the size of 150 micrometer. You can able to create a lot of fins inside the channel, and that can trigger a lot of heat transfer area, that can trigger a lot of nucleation sites, and that can able to cool the device effectively. This is one of the method. The structured microchannel provided with lot of stable nucleation sites by providing a lot of tiny cavities and introducing the wicking effect. It can able to accumulate the water easily towards the surface, and it can able to enhance the performance. These are called micro fin enhancing the heat transfer of microchannels. You can see the literature from some researcher. Drastic. This is the normal microchannel. This is the microchannel case with pin fins. You can see a drastic enhancement in the heat transfer coefficient here. This is the one method to improve the heat transfer coefficient in channel. Different types of fins are available. You can see stepped fin, you can see piranha type fin, you can see some cavities has been built on the channel in order to stimulate the heat transfer, in order to create the nucleation, different profile, trapezoidal, elliptical, triangular, or in some reentrant channel. The main aim is to stick the water maximum to the surface without dry out, so that it can automatically able to enhance the heat transfer. And some has been introduced wavy channels. You can say these wavy channels will introduce some secondary flow passages inside the waviness, and that will enhance the boundary layer and will mix the fluid and will enhance the heat transfer. Like that also some researches are coming. This has been already published in 2020 here. And so a lot of things you can adopt, you can think of in order to enhance the heat transfer like this, and which can be applied in the miniature channels. The target may be towards electronic cooling or some other cooling, whatever it is. So the main research scope behind this was this optimization of pin shapes. We need to optimize the shape so that maximum heat transfer will be there. And the geometric parameter selection, which geometry, whether it is trapezoidal, whether it is a circular pin, whether it is rectangular, all things need to be optimized. Next one, the interdisciplinary approach. You can be linked with a production engineer or some metallurgical or with some other manufacturing engineer, so that you are working in the heat transfer part and he or she may be working in the machining part. So you can collaborate together and you can develop some sort of new fin structures that can enhance heat transfer. So it's an interdisciplinary field of work, and interdisciplinary research scope is also there. So we need to be economic and long-lasting structures need to be provided. So all these things can be, a manufacturing person can be involved much more. So these are the research scope that are available in case of improving the heat transfer from the microchannel surface by using pin fins. You can think about all these things. Which type of pin can able to improve the heat transfer like that? So one category of research. Next is the flow boiling instability. We have already mentioned that microchannels can be used in cooling of the channels because two-phase flow is more effective in cooling. Similarly, there are a lot of issues associated with that. The main issue is that instability. Instability means you can see the channel size is very small. It's nearly 0.5 mm or some 300 microns. In the micron scale, the channel size. Suppose it's undergoing boiling inside the channel. One bubble, it is there. It is formed here and it is allowing to expand. There is a flow here which may not be sufficient enough to carry this bubble towards the outlet. What will happen then? Here it is. It will allow to expand in the both directions, this direction and this direction. So what will happen is there is a sudden increase in the pressure inside the channel. You can see when the nucleation occurs, there is a sudden increase in the pressure and there is a sudden decrease in the pressure. Once this is moving out, the pressure will decrease. So there is a drastic pressure changes inside the channels. This is what called as instabilities. There is a drastic increase in the pressure. There is a drastic reduction in the pressure. In that way, this vapor will oscillate inside the channels, and that will create an immense pressure drop and immense temperature fluctuation inside the channel. And entirely what will happen? Your processor will also get affected with that. So this is the main issue behind the microchannel cooling. One of the main things that to be addressed in case of microchannel based two-phase cooling. This flow instability must be avoided at any cost. How we can avoid this instability? One way is we can pressurize the pump more. So we can pressurize, okay, we can pressurize, you can push the fluid, you can push the vapor out. So what will happen? More pumping power need to be employed. So power consumption will increase. So we need to avoid that also. We need to reduce the flow instability with less pumping power. So what's the option? The research ideas, a lot of research ideas has been involved in that. You can see inlet restrictors. One of the inlet restrictors, they will allow a small notch-like structures on the inlet here. You can see a small notch-like structures. This will allow the backflow. When the flow is coming back, here there is only a small restriction. So it will not allow the flow, but definitely this will increase the pressure drop, but not as much when compared to increasing the pumping pressure. So in this way, we can able to regulate the flow instability. You can see here also a lot of flow instability. You can see here a lot of notch-like structures here. A sudden restriction in the flow will occur, so the fluid will not be coming back. So instabilities can be regulated. So the next one of the interesting thing is that re-entrant cavities. You can see this is the channel wall. This is the channel wall. You can see this is the channel pathway. On the side wall, you can see a lot of small structures has been built or cavities has been built. What will happen when the water is or the fluid is boiling inside the channel? This vapor will be occupied in these cavities. You can see a top view of that. You can see here. When the fluid is flowing through the cavity, when the bubble is formed, this bubble will go inside the cavity. It will not be in this mainstream. So there is no obstruction. So the flow can be easily moved and it can able to cool the device, while the bubble can be trapped inside here, which can be later removed during one stage. Okay, this is what called as reentrant cavities. Next is offset strip fins. Strip fins has been used to in order to churn the boundaries actually, but here when the bubble is formed here, these strip fins will cut off the bubble. It will cut all the bubbles. All bubbles has been interacted with these strip fins, and it will split the bubble to two bubbles. Again, it will get splitted like that. On the passage, the bubbles will get splitted, and larger bubbles will be splitted to smaller bubbles, and it will not create any disturbance to the flow, and like that the flow will continue. So all these methods has been achieved better heat transfer coefficient, but the main disadvantages is that highest pressure drop that is unavoidable. So the researchers are thinking about a method with lower pressure drop and more performance. So there comes the another idea, that is what called as open micro channels. You can see these are the channels on the bottom, and you can see a small cavity on the top here. This small cavity on the top will reduce the hydraulic diameter. Anyhow, it will reduce the transfer coefficient. But what will happen to the bubble? You can see here, the bubble will be developing on the surface. Suddenly, it will be jumping to the top here, and it will occupy the space. You can see the space that is occupying on the top. Then what will happen? The bottom surface is free. It is free to move, or it is free to fill with the liquid, and the entire thing will get cooled efficiently. So in this way, the open microchannel can able to reduce the flow instabilities with the lower pressure drop. But since the gap will introduce a higher hydraulic diameter, the heat transfer coefficient will be a little bit less. So we have also some sort of experiment with that type of open microchannel. You can see the view of an open microchannel. See, the bubble is occupying to the top. See, the bubble is occupying to the top surface without any hindrance. You can see here the mechanism. Bubble is developing, the bubble is lifting off, and simply it is occupying on the top without disturbing the channel. See, like this. So in this way, you can able to improvise your channel and make it more effective. So these are the innovative researches has been introduced by many persons in the same area of microchannel heat transfer improvement. You can see expanding channel. This expanding channel is an interesting thing. You can see it's an increasing cross-sectional area throughout the length. It is used to cool electronic devices. The heat from the device is coming here, and while boiling, the larger bubbles will be simply moving out like this, because it has a gradual expanding area towards the outlet. So it will be moving towards the outlet. No backflow will be coming since the cross-sectional area here is very less. So one method. The next one is the stepwise channel. The same concept only, increasing the cross-sectional area towards the outlet, and it can be freely move the bubbles towards the outlet. And this is one of the newest combination, that is hybrid configuration. You can see here, half portion is channel and half portion is simply a plain surface. That will also reduce the instability, because up to this point, the bubble will come and simply it will throw off the bubble towards this small gap, and it can able to remove easily. So this is a hybrid configuration. In this way, you can able to think about different arrangements of channels and construction of different structures on the surface, so that the flow can be stabilized well for a cooling device. In that way, the research can be moved forward, and you can able to find some innovative method in order to find a better cooling scheme. All these are patented. You can see this expanding microchannel concept has been patented. This hybrid configuration has been patented. Everything has been patented by one of the researchers. So you can also able to think of one, and you can also able to move ahead with a good result. The next important thing is the wettability. Actually, this wettability has a major role in this cooling, because how the water or how the fluid wet the surface is important in cooling. If it is more wet the surface, it can able to dissipate, or it can able to spread more, and it can able to absorb more heat from the surface. It can prevent dry out. In this way, this wettability has a huge role in boiling heat transfer and also in electronic cooling also. This wettability can be improved by different methods. You can see a lot of wettabilities can be improved. You can adopt some porous coatings. These metallurgy persons and all, they have very much interested in this area, porous coating. Some sort of porous coating, alumina porous coating, some copper porous coating, some porous surface can able to penetrate water or the working fluid towards the heating surface, and that can able to enhance the heat transfer and prevent dry out. So you can think about that, some sort of surface that can able to uh, improve the wettability of the working fluid. Okay, simply by changing the roughness also you can able to change the wettability. This is a uh, schematic that showing that simply changing the roughness will change the wettability. Here you can see it is completely wetting, here it is not wetting, here it is not at all wetting the surface. And some micro nano structures on the surface, some small nano profiles can be created on the surface, and that can able to penetrate water and that can able to wet the surface properly for a cooling device. So in this way also you can able to think about some micro or nano scale structures. And one of the innovative research, that is carbon nanotube CNT coatings. The CNT coating having extreme good performance in case of wetting, because it can able to wet a lot the surface, it can able to penetrate the water completely, and it can able to enhance the heat transfer. So in this way you can able to design your surface, and you can design the surface for particular application, even if it is for heat transfer enhancement or any other purpose. You can adopt the same into the cooling technology also. So what are the different possibilities in wettabilities? You can study the durability test, you can study about the addition of the coatings, you can test aging, you can mix the different patterns, hydrophobic and hydrophilic patterns, you can mix it with different patterns. You can play with bubble dynamics, micro layer evaporation, you can report temperature profile, and different methods has been developed, because this photolithography, laser beam machining, some spray method in order to coat something, this everything can be evolved. But one of the innovating area in this was its biomimicry. Actually, this some biologically inspired materials. For example, this lotus leaf. This lotus leaf, it having a very good hydrophobic surface. It will not allow the water to touch the surface. Like that, some bio-inspired surfaces may be there. You can adopt the bio-inspired surfaces into this boiling surface or into this channel surface, and like that you can report a new way of improved method of electronic cooling, or improved heat transfer coefficient, or improved wettability. In that way you can also explore. A lot of publications are coming like that, with a bio-inspired adoption of some methodology into that practical application. So you can also think about that. Next is the working fluid. As previously I have mentioned, this working fluid has a huge role. If we use water, it has a good performance, high surface tension, high latent heat of vaporization. It can able to easily bubble depart. But the problem is that this dielectric constant, when it is mixed with one electrical field, it will create a lot of problems. So we will generally prefer refrigerant, even it is having very low performance factors. So the research scope in this working fluid area is that you can try different binary mixtures, because water itself is difficult, its performance is high. By allowing a combination of these two, this water along with some electronic fluid, that means some water ethanol, in that way you can create some binary mixture or tertiary mixture, that can some ionic solvent also. You can able to create one binary mixture, and you can experiment in a channel, and you can find out that it has a good performance. In that way you can explore. Next is self-reverting fluid. Some fluid we can able to revet the surface properly. You can find out some self-reverting fluid combination, and you can trial that also. The another important method is that adding surfactants. Some chemicals like sodium doxysulfate, SDS, it can able to change the surface tension of the water. If the surface tension is changed, the water will become more wettable or less wettable. Like that, you can play with this reduced surface tension or higher surface tension. What's the impact on heat transfer? Like that, you can test. So adding surfactants is another method. So different category of surfactants, ionic surfactant, are there, different categories there. You can explore in that way towards this working fluid methodology in cooling effectiveness. This is another method, that is nanofluids, because nanofluids can also able to increase the heat transfer performance effectively, because these small nanoparticles can improve the conductivity. But for boiling case, this nanofluid is not recommended. For two-phase cooling, this is not recommended. For single-phase cooling, it is okay. Why it is? Because some nanoparticles will deposit on the surface and it will hinder the boiling. It will not allow the nucleation sites, or sometimes it will allow. So its performance is not a constant one as far as boiling two-phase flow is considered. So it is not recommended as far as my observations, and regarding our work with nanofluids, it is not that much recommended from our side, but it is reported in literatures regarding nanofluid two-phase flow. It is reported, and some persons has been reported with enhancement, while some others with degraded performance also. Next is the gravitational orientation studies. Actually, this electronic cooling is meant mainly for this cooling of avionic devices. You have know that in spacecraft and all, it's very difficult to cool the module or the electronic devices. A lot of electronic devices and processors are there. So cooling that by using a bigger fan or a bigger heatsink is very difficult. So they rely mainly on these miniature small flow loops. So in these cases, this two-phase flow has a big importance because it can able to dissipate a lot of heat. But the main problem is that boiling. When we are staying in the earth environmental condition, it is easy to boil because bubble will be moving from the surface. So what will happen in space? If we leave the gravitational environment, the bubbles will not be moving easily from the surface due to the lack of the gravity. So bubbles will be sticking on the surface, and that will degrade the surface, and hence the heat transfer coefficient will reduce. So usually these test has been conducted by using some parabolic flight test, some drop tower and other things. By using this parabolic flight, the experiment will be conducted, but the time seconds for that is very, very small. Around 22 seconds you will get for a parabolic flight test, and for drop tower 10 seconds. Thinking of an experimental condition within this time is very difficult. So in order to test some device in different gravity, what we will do is we will tilt the orientation. We will tilt with different orientation, and we will employ some adverse gravity environment. You can see here, this is against gravity, this is towards gravity. In that way, we can change the orientation of the channel, and you can find out the performance variation. This is actually my area of the research, and if you are interested, you can focusing on different channel sizes with different orientations and different configurations. So how effective it is performing in these different orientations, like that you can able to study. And till now we are discussing with the experimental part, but for persons who are not reaching and towards the experimental, and if you are powerful in your more in your mathematics and coding part, they can able to think of computation fluid dynamics approach in order to solve this electronic packaging or electronic cooling problem. Actually, the main thing behind this two-phase flow modeling is that a lot of flow patterns are coming. You can see bubble, slug, annular, like the different flow patterns are coming on the way. So modeling all these things in a single cluster is difficult. So what researchers are doing, they will model independently. So for bubbly flow, one model; for slug flow, one model; for annular flow, one model. Like that, they will do. They will assume the flow as a homogeneous bubble, slug, or annular. In that way, they will model. Till now, there is no generalized solution for a continuous modeling of all these flow patterns. Independently, we need to model. So these are the modeling of a flow through a channel, flow through a small channel by using a CFD analysis. Definitely, you need to write some user-defined functions in order to trace this bubble moment, in order to find out how the bubble will behave inside the channel, at what radius it will departure. There is some equations available, the bubble departure diameter equation. So that things you need to be written in the user-defined function, and you need to be solved so that it will model it accordingly. In that way, you can do the electronic cooling analysis by using the CFD method also, if you are interested in that area. So I think we can conclude now, because telling a lot of things in a fraction of time, it's not important. I think you will get a basic overview on how to start with these things as far as from this previous slide. Actually, this progress behind this chip packaging is advancing day by day, and the thermal management requirement is also very high. So each segment of this thermal management system market is evaluated by the research industry. So each and every component adaptation will be studied by the research labs before implementing directly. So there is a huge research scope in this area. I think this microchannel cooling technology is also emerged like that. From 1960, it was Tuckerman and Pease only demonstrated first. Till this 2020 also, publications are there coming with a lot of innovative methods of cooling. So I think we can also able to have some more knowledge on this at a later time. Meanwhile, you can explore more on this area of research. These are some of the publications from our team regarding the same electronic cooling and some micro mini channel based studies. And I will refer some textbook if you are interested more on this area. The first one is that heat transfer and fluid flow. It's one by the Kandalikar, who was Dr. Kandalikar. He's a professor and he's a professor in Pune University and all, Gerimella also. You can refer to this textbook. They are very, very interesting textbooks. They are pioneers in this area of mini micro channel based cooling. They have a lot of patents in this area. So it will be better if you go through this textbook regarding mini channels and micro channels. And if you are interested in the two-phase flow of miniature channels, you can also refer these books. This is also by Professor Kandalikar, boiling and condensation. Similarly, if you want the strong basis of convective boiling and condensation, you want this book, John G. Collier. All these are readable books, which is worth in this area. If you can get a free time, you can try from your library. And these are some references. And thank you for staying there for a long time. Thank you. And I also recommend you to stay well and avoid the spreading of this COVID-19. It's become a pandemic now, and use the things, wash your hands, use the coughing acuity, and keep away from outside as far as possible. Thank you.
This is the feedback section. Any questions, please?
Hello? Hello? Hello?
It's audible, Ajith.
Okay, fine.
One question is posted in chat box. Can you
can you just explain that? Because a lot of things are coming inside.
Okay. Dr. Ajith,
yeah,
there is a question from while doing the CFD analysis, whether need to consider the slip condition or no slip condition inside the channel. Similarly, how to identify for fully developed flow in channel for micro channel.
Yeah, actually, this condition, we don't need to consider the slip condition, because here, in case of micro channels, first you need to check the Knudsen number. because we are analyzing all these things by assuming that the flow is continuous. That is, the continuity equation must be valid. So in the continuity equation is valid, the Knudsen number is definitely in that range, and you no need to consider the slip condition. If your channel size is in the nanometer range, definitely the Knudsen number you need to check. And if the continuity breaks, then you need to consider the slip condition. If Knudsen number is within that continuum, if you can assuming that as continuum, then no need to consider the slip flow inside the channel. Usually micro channel definitely in the range of 100 micrometer to above 100 micrometer, I think slip will not affect. If you are reducing below that, definitely you need to incorporate that slip condition.
Okay,
Yeah.
thank you. Second question is from Srikumar Ian.
Yeah.
Okay, what about the material used for heat sinks? And what are the material requirements for a heat sinks? Effect of heat sink material on heat transfer?
Yeah, actually, regarding the heat sink, there are two aspects. One is thermal performance, because if you are targeted in order to improve the heat transfer, you can use copper. But if you are familiarizing with the cost part, copper is costly and its density is very high, so it will make your system more bulk. So it's your requirement, it's your customer requirement, or it's the design requirement, whether you need an optimization in cost, whether you need an effectiveness in the weight, whether you need an effectiveness in the thermal conductivity of the material. So generally aluminum was used in heat sink. Nowadays some advanced materials such as aluminum, combination of aluminum heat transfer. But in some heat sinks, copper also found. It's the choice of the designer's choice actually. If copper is used, more the heat will be dissipated because it has very good thermal conductivity. If aluminum is not having much, so it's the choice. It's the choice actually. For laboratory test, you can use copper because we are not implementing directly into a electronic system. It's depend upon the weight and all. You need to think about a lot of parameters before deciding that question.
Okay, another question from same Aminar sir. Whether the flow will be fully developed always in the microchannel?
Yeah, generally it will be, but you need to check out with the normal equations for conventional channels, 0.05 REDPR, like that. You need to check it out, and some length you will get. In that length only, it will be fully developed. Usually for conventional channels, we will adopting the length of hydrodynamic boundary layer development. We will use based on the conventional channels only. There is no separate equation. 0.05 RED, the same equation we are using. Fully developed hydrodynamic length, you will calculate by using the same. In that way, you can find out based on the channel length, based on Reynolds number, and based on Prandtl number, you can calculate the fully developed length. At what point it is fully developing, you can calculate using that equation. Thermally developing or hydrodynamically, both you can check. One is Prandtl number will come into picture. Otherwise, 0.05 RE into D only will come. Like that, you can calculate. No issues.
Thank you. Another question from Jinsha. What are the methods used to machine microfins in the micro gap?
Microfins, yeah, actually, one method is laser machining, because this laser machining can able to create microstructures up to 4 micrometers. By using pulsed laser machining, we can able to create in that much dimension we can able to create. But the second one is lithography. Lithography is a complex method actually. You need to mask the surface with some chemical, and you will allow some light to pass through it, and the masking surface will not be affected, the other surfaces will be affected. In that way, you can able to machine small micro surfaces in the micro channel itself, or by using laser machining. That's a simple method we have used, or by using small miniature tools also, pinpoint tools also, you can able to create a better laser machining. Yeah.
So what is homogeneous flow process?
Hello?
So what is homogeneous flow process?
Yeah, actually, while two-phase flow, you can see that different flow patterns are coming. Bubbly flow, annular flow, slug flow, like that. Okay. While modeling, it's difficult to incorporate all the conditions in your domain. So what we will assume is the entire flow inside the channel is a single flow. That means either it is bubble flow, either it is slug flow, or either it is annular flow. In such way we will define our model, and such model is what called as homogeneous, where the pattern is homogeneously throughout the channel was same. That's what we called as homogeneous model.
Thank you, sir. Thank you.
Yeah, fine.
Okay, next question from Ritvik. So what are the different types of liquids used in immersion cooling?
Yeah, definitely it will be fluorinert FC72 HFE, which having very good dielectric strength, and definitely it is not water. Dielectric fluid, or we will say electronic fluid, that will not split or will not break down under the application of electrical field. And we must be very careful that no corrosion materials, dirt, dust, nothing will be there inside that fluid. It must be completely clear when used for immersion cooling. I think the next session Uday will deal much more with that.
Sir, can I ask?
Hello?
Sir, I have a question.
Yeah, you can ask.
Sir, how this test section is fully tested in experimental setup before it is inserted into the electronic device?
It's not clear. The first part is not clear.
So I
Can I
have
just...
got the message box. How the test section is fully tested in the experimental setup, and
How
before it is
the test section is fully
tested.
okay? You are asking about
Inserting it into the electronic device. So what parameters or perspective we are looking into?
oh yeah, actually what our main target is to cool the processor. We need to cool the processor by using something, whatever it is. Because initially, if we are directly allowing some liquid to pass through the processor, or if we create a processor or something based on our initial requirement, it may not be success. It may end in failure. Sometimes leak will occur. If the water is flowing, some machining parameters, some arrangement problem will cause leak. So your entire electronic circuit will going to vanish. So initially what we will do is we will create a test section. Test section means it's simply a replica of your processor in the thermal point of view only, not in the electronic point of view. It can allow to heat, it can allow to cool, like that. A lot of thermocouples you can build. So usually copper will be used instead of the processor, and the copper we will heat externally by using some heater. We will heat it so that it will simulate like a processor. As simple as the processor is heated, like that here the copper is heated. Then we will allow the water or the liquid to pass through the surface, and the main parameters that we are checking is the temperature. For a particular flow rate, what will be the surface temperature for a particular heat flux? Suppose a processor is operating at 84 watts heat dissipation TDP. We will set 84 dissipation in the heater of our DC power supply. So it will simulate 84 watts exactly to the copper. We will allow at a particular flow rate, so we can expect what's the temperature is on the surface. In that way we can simulate. We can expect the pressure drop, so we can calculate the pumping power. So all these parameters we will look. What's the outlet temperature? Whether it will be cooled externally, or whether it can be recirculated back. Because all these parameters we will observe. Then, if it is every part is okay, we will adapt the same on your processor. We will simply make some machining parameters or heat sink on the top of the processor. We will remodify the top surface of the processor with the help of some electronic hardware person, because some other things has also to be included in that. In that way, we will find solution. So it's simply a replica of the processor, simply a replica of heat generation from the processor. I think it was clear.
Thank you.
Yeah.
Okay, another question. What will the temperature affect the normal behavior of semiconductors? Will the temperature affect the normal behavior of semiconductors and how?
Definitely. Suppose, for example, we'll take the processor itself. Actually, each processor, when you look to that specification, there is a one parameter what called as a TDP, thermal design power. This thermal design power is the average power that a processor will dissipate when it is operating at a base gigahertz, that is base frequency, with the company provided working load. Some if it is Intel will provide some working condition. In that working condition, if it is operated at this gigahertz speed, how much heat will be dissipated from the processor? That is what called as TDP. Suppose it is 84 watts. If you trigger the processor more, if you are doing a lot of multitasking, watching movies, designing something, the load on the processor will increase. So there is a safe temperature also you have given. It's maybe 84, it may be some 93 or somewhat. If it increases beyond that temperature, the first thing is resistance. The semiconductor resistance, it will increase almost all with the temperature. As far as my observation, its resistance will cause more heat generation and will make the current flow. It will not allow the current flow properly and it will damage the system. The other thing is that there are a lot of circuits in your device which was soldered by using solder, and its melting point may fall in that range, in that 105, in that range, I think. So that also will cause melt, that also will create problem. And the other thing is that these 7 billion transistors are working as a binary 0 and 1. It will allow current 1, if it not allow current 0. So what will happen if a lot of transistors are there, and if you getting the heat more and more, it will affect the functioning of the other transistors also due to the variation of the resistance. So definitely the temperature will cause the performance decrease. For another example, if you take PV cell, photovoltaic cell, it will get the optimum maximum efficiency at a particular temperature only, at 45 degree or 50 degree. If you increase beyond that, semiconductor, its temperature increase means its performance will be out, the current and voltage will be less. So that also to be cooled properly, we cannot increase the temperature of a PV panel also beyond a limit. So definitely temperature affects semiconductor. I think an electronic person can explain more regarding this part, how it will affect. They can only explain, but definitely it will affect. I think it was clear.
Okay. Next question. Can we use deionized water as working fluid in the mini channel cooling, which is the preferred geometrical shape of a pin? What can have better heat transfer rate?
Two conditions. One, they are using deionized water. What's the second one? What's the difference between? Can you just read once more?
Can we use deionized water as working fluid in the mini channel cooling?
Yeah.
Which is the preferred geometrical shape of a pin? What can have better heat transfer rate?
Okay. Yeah. First question is regarding whether we can use the deionized water. Yeah, you can use deionized water in a electronic cooling device. There is no issues in that, but ensure that water is not directly contacting the processor. By using some device only, you are touching the processor. By using a heatsink only, you are touching the processor. As I was explained, the water is having a dielectric constant very high. That means it can able to polarize and it can lead to breakdown, because the dielectric strength of water is very less. So what will happen is, if you are using at an extreme power situation, this water will break down. It will break down and it will get polarized, and it will allow the electric field to conduct. So the net effect is the damage. So that's why water is avoiding. But many researchers, even me also, trying with water. Why? Because it has an immense specific heat, nearly 4 times higher than some others, nearly very high CP, 4.197 kilojoule per kilogram Kelvin. You can able to remove each with every kilogram. Yeah, it's good. Conductivity also good. Surface tension, bubble dynamics, everything was good. The only drawback is that dielectric strength. If you can able to avoid it any means, if you are damn sure that it will not cause any issue to your electronic device, you can employ, no issues. But generally, it is not recommended in practical applications. In lab applications, it was okay. And the second question, the best fin, it's the research point of view. Till now, no answer. Because each and every fins has its own performance. We need to think a lot of things beyond telling an answer to that question. Its boundary layer, its height, its width, everything. But its pressure drop also need to be considered. Giving a lot of fins to a surface will not improve the heat transfer. There is a factor what called as figure of merit. The amount of cost you invested to create that to the output and pressure drop. That thing also to be looked before telling an answer to that. We cannot answer directly what fin will be best like that. But theoretical point of view, you can learn from heat transfer textbook that this parabolic fins and all will be effective. Triangular fin is more effective than rectangular fin. Like that we can say. But practically, it's not possible. It may, practical application, it may create some other issues. Machining will be very difficult. So which fin will give better performance, you need to try and found. It depends upon your test section, your experimental facility. A lot of things will depend. Theoretically only we can say. Experimentally, you need to done it and prove it. That's all. I think it was clear.
Okay, thank you.
Yeah.
So we are winding up this section.
Yeah.
On behalf of Department of Mechanical Engineering, Jyoti Engineering College, we extend our sincere thanks to Dr. Ajith Krishnan for a wonderful presentation. It is very informative and helpful to understand the micro and mini channel cooling. Thank you everyone for your active participation and make this section a good success. Our next section will be handled by Dr. Uday Kumar ji on topic pool boiling in electronics cooling sinks. The next section will be at 3 p.m. Hope all of you will be there. Thank you. The meet ID will be same.